Hi everyone, Miss Lorette here. In this video I'm going to be walking you guys through section 6.5. This lesson is all about how to write and graph linear inequalities. So it's assumed that at this point you've covered everything in chapter 5, which is all about how to write and graph linear equations. Linear inequalities is not that much different. So a lot of the skills that you learned in chapter 5, you're going to use them here. So let's go ahead and get started. The first thing that we're going to do is determine if an ordered pair is a solution to an inequality. You may have done this before in chapter 3 for inequalities that had just one variable, or you may have even done it in chapter 5 for linear equations. In order to determine if an ordered pair is a solution to a linear inequality, you're going to take the ordered pair, the x and the y, you're going to replace the x and the y in that inequality with the numbers from the point, and you're going to evaluate. And at the very end, you're going to have some sort of inequality that you have to determine if it's true or false. If the inequality you're left with is true, the ordered pair is a solution. If the inequality you have is false, the ordered pair is not a solution. So I'll walk you through a couple of them and then I'll give you one to try. So we've got the ordered pair 1, 2. Here's my x, here's my y, and then we have the inequality y is greater than x minus 3. This looks very similar to a linear equation in slope-intercept form, in the form y equals mx plus b. All I do is I replace the y with the 2 from the point. I'm going to copy down my inequality symbol. We need to be really careful now not to inadvertently change it to equal sign since we're probably used to equations. I'm going to replace the x with a 1 and then bring down that minus 3. Now I just evaluate what's on the right. 1 minus 3 is going to give me a negative 2. So this inequality reads 2 is greater than negative 2. That's actually true. 2 is greater than negative 2. Okay, so be careful. We can't just assume that it's false just because we don't have the same number on both sides. This is not an equation. This is an inequality. 2 is greater than negative 2. All positives are greater than negatives. So since this is a true inequality, 1, 2 is a solution. Let's try another one. We have the ordered pair negative 3, 4. So here's my x, here's my y. And we have a linear inequality that kind of looks like a standard form equation. ax plus by equals c. 4 times x is going to get replaced with 4 times negative 3. Plus y becomes plus 4. And then I bring down the rest of my inequality. I have to multiply first before I can add. So I'm going to multiply and get negative 12, and I'm going to add those results together and get a negative 8. So we have negative 8 is less than or equal to negative 10. Okay, remember that bar means or equal. So only one of those statements has to be true in order for the inequality to be true. Well, negative 8 is actually not less than negative 10. Be careful, these are negatives. If they were positives, if it was 8 and 10, then it would be true. But negatives are the opposites to positives, so they work the opposite way. The number that you would think is actually smaller is actually the bigger number because it's closer to 0. This might be easier to see on a number line. If I drew a number line really quick, and here's 0, here's negative 8, and then 2 spaces away is negative 10. This negative 8 is a little bit closer to 0, therefore it's actually greater than negative 10. So this is a false statement, and they're definitely not equal. So this is a false statement. So negative 3, 4 is not a solution. Here's one for you to try. I encourage you to pause the video here, give it a go, and then I'll show you the answer. All right, so here is the solution that I'm getting. This looks like a linear equation in point slope form. So it's a linear inequality in point slope form, and we're testing the point 3, -1. So we're replacing that x with a 3 and replacing that y with a -1. Careful not to drop your parentheses too early. We want to evaluate what's in there first. I can evaluate what's on the left as well. And then I multiply to get a negative on the right. So this inequality reads 1 is greater than or equal to -2. Even though they're not equal, 1 is greater than -2. Remember, only one of those statements has to be true in order for this inequality to be true. So since that is true, this ordered pair is a solution, and hopefully we matched. Now let's talk about how to graph linear inequalities. Again, at this point you should already know how to graph linear equations, so to start, it's going to be the same concept. The first thing that you're going to do to graph what's known as your boundary line is you're going to plot the points like you normally would as if it was an equation. It's really a good idea at this point to plot as many points as possible. In the past, I would say, 3 points is sufficient. Maybe you have a different teacher that says 2 points is sufficient. At this point, I always encourage my students, plot as many points as possible, so that way your graph is going to be very, very clear. However, do not connect the points with a line yet. You have to determine whether or not to connect the points with a solid line or a dashed line. Okay, so think about when we graphed inequalities all the way back in chapter 3. If there was no bar underneath our symbol, when we graphed that solution on a number line, we used an open circle because we didn't want that number that we were graphing to actually count. It's kind of the same idea when we're graphing linear inequalities. If we have some sort of symbol that does not have the bar, we don't want the ordered pairs on that line to actually count. But instead of using open circles, we just use a dashed line. If we do have a bar under the symbol, that means that all of the ordered pairs along that boundary line are going to count as solutions in our inequality. So we want to use a solid line. This is similar to when we would color in that circle on a number line. And then here's the part that can be a little tricky for some students. There is a shortcut method to doing this step, but I'm going to teach you the foolproof method because it'll work regardless of what form the inequality is in. The shortcut method only works if the y value does not have a negative coefficient sitting in front of it. So when we're graphing regular single variable inequalities on a number line, after we chose the type of circle, we needed to shade that number line either to the left or the right, depending on where our solutions were. It's a similar idea for when we're graphing linear inequalities. We're going to have to shade a portion of our graph. So we call that portion of the graph the half plane, even though it might not look like exactly half. We call it the half plane. And the easiest way to do this algebraically is to select a point that is not on your boundary line, because again, those points might not be solutions anyways. Also, if we're on the line, that's not going to tell us which half plane to shade. We want to be off of the line. I think the point 0, 0 works best when it's available, okay? Sometimes this ordered pair is sitting on the boundary line, so we might not be able to use it sometimes, but if it's not sitting on that boundary line, if it's sitting in one of those half planes, I think this is the easiest ordered pair to test out. And you do what we did on the previous slides, where we plug it in and determine if it's a solution. If the ordered pair is a solution, we're going to shade the half plane that actually contains that point. If that ordered pair is not a solution, we're going to shade the half plane that doesn't contain that point. So we're going to shade the other half plane. Now, I just threw a lot of information at you, and you're probably not sure what a lot of it means. So let's put it to practice so that way you can understand it a little bit more. I'll do several graphs with you, and then I'll give you a few to try. The first thing that I need to determine is what form is this inequality in, because that's going to help me graph it. Well, this is in point slope form. That means that I have a slope of 1/2, and I also have a point at -4, 2. Okay, again, I'm assuming that you've covered all of these forms and you understand how I got that information. The next thing I'm going to do is what step 1 said to do, and I'm going to plot as many points using this information as I can. I'm going to start at the ordered pair -4, 2. I'm going to rise 1 and run to the right 2. I can also reverse that direction once, and from that starting point, I could have gone down 1 and left 2. Now, before I connect these points, I need to look at the inequality symbol to determine, do I connect them with a dashed or solid line? Well, the bar underneath tells me I want all the points along the boundary line to count. So I'm going to connect with a solid line like we normally would. Now I need to determine which half plane to shade. I either have to shade this entire section, which looks like a triangle. I need to either shade this half plane, or I need to shade this entire half plane on the other side of that boundary line. Again, in order to do this, we need to pick a point. Any point that's not sitting on that line will do, but I think that the ordered pair 0, 0 works the easiest. So I'm going to test the point 0, 0. I'm going to substitute it into this inequality. So it's going to be y, or 0 minus 2 is less than or equal to 1/2, open parentheses, 0 plus 4. And I'm just going to evaluate. Whoops, it's not a negative, it's a positive. And half of 4 is 2. So this inequality reads -2 is less than or equal to 2. Well, they're not equal, but -2 is less than 2. So that is a true inequality. So what this means is, here was the test point that I picked. What this means is that this half plane, which contains this test point, the half plane is all of this section here. I'm outlining the region right now. That's the region that contained this point. Since the inequality resulted in a true statement for this point, this is the half plane that I shade. So I'm going to shade to the best of my ability this entire region of my graph. And I think it goes without saying that if you're someone who likes to use ink pen on your notes, it's a good idea to use pen, because if you make a mistake on these graphs, you're going to have to scratch it all out and start over. It's better to erase and save a little bit of paper here. Okay, let's do another one. This inequality looks like it's in standard form. I can actually graph using intercepts. So my x-intercept, if I plug 0 in for the y, that's going to leave me with the inequality 3x equals -6. I know I changed it to an equal sign, but I'm just trying to find the point right now, and I don't want that inequality symbol to mess me up. So I'm just trying to find that point. X would equal -2. So I'm going to plot an ordered pair at -2 on the x-axis. I'm going to move this a little bit to the side so I can find the y-intercept. If I want to find the y-intercept, I plug in a 0 for the x. That's going to leave me with 2y equals -6. Again, I'm just changing it to an equation for right now to find the points. That's going to give me a y-intercept at -3. So here's my y-intercept. Now, I mentioned before that it's a good idea to plot as many points as possible. Well, now that I have 2 points on this graph, I can find the slope between the two of them and then use that slope to plot however many more points I can fit. Well, the slope between these two ordered pairs is definitely going to be a negative. I go down 3 spaces and then to the right 2. So my slope is -3/2. So I'm going to start at that x-intercept and go up 3 and left 2. And I can do it one more time. Up 3, left 2. And I can go to that y-intercept and go down 3 and right 2. So even though it's in standard form and I didn't know the slope looking at this inequality, I can plot those intercepts and then use those points to help me find a slope. Now again, before we connect, we need to look at the inequality symbol. It doesn't have a bar underneath. This means I want to use a dashed line, okay? So we're not actually going to connect these points with a solid line. We're going to do a dashed line. And again, I want to pick an ordered pair that's not on that boundary line to determine which half plane I shade. If I pick the point 0, 0, and it ends up being a solution, that means that all the points in this same region are solutions. So I would shade this entire half plane. If I plugged in the point 0, 0, and it's not a solution, that means that I don't want to shade this half plane. I want to shade this other one that kind of looks like a triangle. So again, it doesn't matter which ordered pair you use, but I like using 0, 0 because it's the easiest. I'm going to plug in a 0 for the x, a 0 for the y, and this is greater than -6. 3 times 0 gives me 0. 2 times 0 gives me 0. 0 plus 0 is 0. And this says 0 is greater than -6, which is true. This is a true statement. All positives and the value 0 will always be bigger than -6. So that means that since that point, which is in this region right here that I'm shading, is a solution, all the points in this region are going to be solutions. So I'm going to shade this entire half plane. Whoops. There we go. Let's do a couple more, and then I'll give you some to try. Graph the linear inequalities. So we have one that looks like just a regular equation, y equals a number, but it's y is greater than -2. Well, remember that when these were equations, y equals a number is a horizontal line that passes through a y-intercept at -2. So if I plot points right here, here's my y-intercept. Okay, now normally I would just draw my horizontal line through that, but I'm just going to put a few more points along here because again, I don't want to connect just yet. I don't know if it's going to be a solid or dashed line until I look at that symbol a little more closely. So for now, I'm just going to put points. If I look at this symbol, this tells me that I want to use a dashed line because there's no bar underneath my symbol. And again, I want to now figure out which half plane do I shade, okay? Now again, it doesn't matter which ordered pair you use. If I test 0, 0, then I have a y value of 0. And if that ends up being true, when I substitute it in here, this entire half plane contains the solution. So I would shade here. But just to demonstrate that you can use any ordered pair at all, I'm just going to use a random one. I'm going to use this point down here. This is the ordered pair, actually let's use a different one. This is the ordered pair -2, -4. I just want to show you that it doesn't matter which ordered pair you use. It helps us determine our solutions just the same. Well, this is an x and this is a y, but my inequality only has a y, so I can ignore the x value from that ordered pair completely and just substitute a -4 in place of the y. And if I read this, this says that -4 is greater than -2. So think back to the second problem that we did in these notes. -8 was not smaller than -10, it was bigger. It's kind of the opposite here. -4 is not bigger than -2, it's less than. So this ordered pair that I tested right here, which is sitting in this bottom region of my graph, that is not the solution. That means that this entire region does not contain my solution. So I don't want to shade this region I want to shade the other one. So that's how you would do it if your check ended up not working out. If that point was not a solution, you would not shade the region that point was sitting in, you would shade the other one. All right, another one. Y is less than or equal to negative x plus 1. This tells me I have a slope of -1 and a y-intercept of 1. This is in slope-intercept form. I plot the b value first, and I use that slope of -1 over 1 to plot as many other points as I can. Now I'm going to look at my inequality symbol to determine, is this line solid or dashed? Well, it has a bar underneath it, so I want to connect with a solid line. Now I need to pick a test point, plug it in, and see if that tells me that the region that I'm in contains the solutions, if that's the region I need to shade. And again, it does not matter which ordered pair you pick. You could pick this one, you could pick the origin. The only points that you do not want to pick when you're doing this are points that sit along this line, because these points are not in one of the half planes. They're sitting on the boundary. That's not going to give you any information on whether or not you shade this section of the graph or this section. Again, I like to use the point 0, 0 because I think it's the easiest. You don't have to use that point though. If I plug this in and it's true, that means that I want to shade this entire region because this is the region that contains that point. If it is not true, that means I want to shade the other region. So it's going to be 0 is less than or equal to -0 plus 1. Well, -0 is just 0. There's no such thing as a positive or negative 0. 0 doesn't have a sign. And then 0 plus 1 is just 1. And this reads 0 is less than or equal to 1. They're not equal, but 0 is less than 1. So this ends up being true. So I want to shade this entire region here because this is the section of the graph that contains that point. So that means any of these points in the shaded region, if you plugged it in, they would all work. Here are a couple for you to try. Again, start by graphing the linear inequalities the same way that you would if they were equations. Before you connect your points, look at your symbol to determine is it a solid or dashed line, and then use a test point to determine which half plane you shade. All right, so hopefully you've given that a go. If not, you may want to pause the video here because I'm going to show some solutions. Here's what you should have gotten for your graphs. Number 8 is a vertical line that has an x-intercept at 4. So the way you would start it is you would start by plotting some points, right? And before you connect the points, you would look at the symbol. Since this has a bar underneath my symbol, I connected with a solid line, and then I just used the ordered pair 0, 0 for my test. Now, just like when we did y, the inequality that just contained the y, the horizontal line, this only contains an x. So I'm just replacing that x with a 0. 0 is less than 4. They're not equal, but it is less than. So I'm shading this entire region because this is the region of the graph that contains this ordered pair. And then the last one was in point slope form. You should have determined that there's an ordered pair at 5, -2, and a slope of -3 over 1. Plot the points. Use a dashed line to connect because there's no bar. And then when I used my ordered pair 0, 0 here, it came out as a false statement. That means that we don't want to shade this region at all. We want to shade the other region. This is actually the region that contains ordered pairs that are solutions. All right, last thing that I'm going to cover with you, and then we will call it a day here, is how to write linear inequalities from a graph. Okay, and again, you may have done this in chapter 5 where you were writing equations from a graph. It's kind of the same idea to start. I'm going to do a couple with you and then I'll give you some to try. The first thing that you want to do is write a boundary line. And when I usually do this, I typically do it in the form y equals mx plus b. I think that's the easiest way if our y-intercept is at a nice lattice point. But when I do it, when I substitute my numbers in, I first leave a little space here because remember, these are not equations. We're going to have to determine what inequality symbol to use. So let's start by finding the slope and finding the b value. Well, my b value is right here on the y-axis at -4. And if I pick another nice lattice point, here's one, and here's one, and I rise and run, I'm just going to go down to that other point. I would go down 1 and to the right 1, 2, 3, 4, 5 times. So my slope is a -1/5. So to begin my boundary line, it's y, I'm going to leave a space, -1/5 x minus 4. Now I need to determine what type of inequality symbol do I use. The easiest way to do this is if your shading is above the line, you're going to use one of these symbols. Y is greater than, or y is greater than or equal to. If your shading is below the line, you're going to use y is less than, or y is less than or equal to. And the easiest way to determine if your shading is above or below, put your pencil on the line and move vertically in such a way that you reach the shaded region. Well, I just moved up to get to my shaded region. So the shading is above, so I want to use one of these greater than symbols. To determine which one, look at your line. It's a solid line, so I want to use the one with the bar. So my final inequality is going to be y is greater than or equal to -1/5 x minus 4. Let's do another one. Now this one's going to be a little tricky because this is vertical, okay, but there's a trick to it. For vertical lines, we can't use that trick that I just wrote down where you look and see if the shading's above or below, because for a vertical line, we don't have an above or below. We have a left and a right. Let's start by first identifying the boundary line. Vertical lines are going to be in the format x equals a number. And remember, we're going to leave a little space before we write the symbol because it's not going to be an equal sign. Well, I can just use the x-intercept to determine what number I should use for that inequality. It has an x-intercept at a +3, so it's going to be x, some sort of inequality, and then 3. Here's how you determine what type of symbol to use when your line is vertical, okay? You can kind of look at the x-axis as if it's a number line, okay? So treat the x-axis like a number line. And think about how we used to graph inequalities in chapter 3 when it was just a number line. If my shading is to the right, then you're going to use x is greater than or equal, because all of these numbers, if I just looked at the x-axis like a number line, 4, 5, 6, all these numbers are greater than 3. If the shading is to the left, you're going to use x is less than or equal, because all of these numbers on the x-axis, if I looked at it like a number line, they are less than 3, which is this intercept. Well, my shading is to the right, so I want to use one of these greater than symbols. And I want to use the one with the bar again because this is a solid line. So my final inequality is going to be x is greater than or equal to 3. Okay, so that's how you're going to do it. You're either going to treat the x-axis like a number line, and if it's not a vertical line, if it's oblique or even horizontal, you're going to use these strategies here. So I'm going to give you a couple to try. Here's one of them. Pause the video here, give it a try. And here's the solution that you should have gotten. Y is less than negative 1/3 x minus 2. The slope and the y-intercept should be easy to identify at this point. This is the part that is new for us. So if I put my pencil on this line and move vertically in such a way to reach the shaded region, I would have to go down. So that means I want a less than symbol. And I want the one without the bar because it's a dashed line. Here's another one to try. Pause the video here, give it a go. And then here's the solution that you should have gotten. Horizontal lines are in the format y equals a number. Again, you can still use that technique where you move up or down to reach the shaded region. Okay, so figuring out this number should have been the easy part. And then if I put my pencil on this line and move in such a way to reach the shaded region, I move vertically, I would have to move down. That tells me I want a less than symbol and I want the one with the bar underneath it because it's a solid line. So that's it for today's lesson. I hope that you found all of this helpful. If you have any questions, just reach out to me or your math teacher, and I will see you guys next time. Take care.